So this is a phenol molecule. Now we want to understand that what is the reactivity of this molecule and how the electron in this molecule are adjusted. Okay, so this is a little bit cleaner structure, and so we should focus this one. Okay, this is again phenol. These are the same structure, but it is a little bit cleaner, and my drawing is very bad too, sorry for that. So it has a lone pair. Now first of all we need to draw the resonance form of the phenol, then we will be able to understand the its reactivity. Suppose those electrons shift here, these pi electron will sit on this carbon, so the other structure will look like this. And a positive charge will be on the oxygen, okay, and a negative charge will be on this carbon. So in the next structure, this come here and it comes here. And in the next structure, what happens? These lone pairs, they just move here and sit here. So I should write this structure here because of the space. When it comes, it will again move to the oxygen, and you will just see the first structure, okay, but with a little bit difference, because now when those two electrons were there, so a double bond was here, but here the double bond is not here, it is now here, okay. But our aim is not to understand those arrow pushing, because I am not focusing on those things, because many intelligent people have many videos on that things, but my aim is just to make you understand that how the actual structure look like, okay. So these are the resonance form, maybe they are correct, okay. So this one is okay, this is negative, okay, so I should write it negative. All are negative charges. So when this electron sits here, this is negative, this is negative. Now as you look to all those structures, you can see a pattern. A pattern is that this carbon adjacent, or you can also call it an ortho position to this, okay, on the adjacent carbon to the functional group. This is ortho, this position, and this position. So when you draw all the canonical forms, you just see that on 3 position the negative charge is more concentrated. For the negative charge of what? The negative charge of this poor oxygen. But this is again not 100% of the electron are moving inside the ring. A very small portion of the electron cloud is shifted here, okay, and it produces those forms. So now we need to understand that how the actual structure will be for this phenol. As you know that the OH, but they say is an electron donor or electron donating group, because it has lone pair on it. Anything which has a lone pair on it will donate to the ring, okay. So it is electron donating group or electron donor, okay. So because now our concern is that how the actual structure may look like. It should look like this. I am just writing this like this, okay. This is the actual bond and the other one is like this, okay, sorry. So what does this structure say? This is one lone pair, and the other lone pair I am writing it as normal, and the other lone pair is smaller because some contribution goes to the ring. Okay, so for this structure what happens, this is its OH. Okay, now the oxygen and the oxygen of this phenol is not very basic, because its electron cloud, some of its electron cloud, not all of it, is shifted to the ring. But in the ring, as you see, the three positions are a little bit negative. This position, and this position, they are negative. So they say that that's how. But in reality, what is going on? This electron comes here, and then negative charge appear on this carbon as a result of surplus electron, and this moves to here, and another negative charge appear here because of the resonance. Those things doesn't occur. Those things are just to make us understand the actual structure. Okay. This thing is the reality. Those are the tools to make us understand this thing. In reality, this molecule is like this. It is just present like this. Okay, I should erase those things that you may clearly see. So what this structure will tell us, okay, those back and forth doesn't occur, never. Okay, this is again from this structure I made this thing. Okay, so the resonance doesn't occur. We cannot say that these electrons are moving to this place, after that it goes to this place, after that it goes to where, the para position, from this ortho position, and then to the ring. This doesn't occur. In reality, those electrons of the oxygen are distributed or shifted to the ring, and in the ring they are concentrated on these three positions when an electron donor is attached to the benzene ring. So those are not, scientifically those are not that much relevant, but to make us understand, these are relevant for us then, and this is the true structure. Those are the tools or the steps which leads us to the actual structure. Okay, and as you see that this carbon and this carbon is equal, so this positive negative charge, this negativeness or more electron cloud presence here is equal to this one, and this is a little bit different, but you can say that again it is equal to those things. Very little difference between those things. We'll be explaining this in some other subject. Okay, so if you have some base, now electrophile, we will be discussing those things a lot, okay, the electrophiles and those things, but right now we just want to understand the resonance. Okay, this oxygen, though it has lone pairs, it will not attack, because this is not that oxygen which has a full-fledged electron pair, because some of its electrons cloud is lost to the ring, but now the ring is more electron rich than normal benzene. If you compare it with the normal benzene, this ring is more rich. This ring is more rich, electron rich, because it has 6 electrons present in it, normally 6 pi electron, but it has 6 plus some of the electron cloud. So this is more electron rich ring. So what happened? Now the oxygen will not attack this thing, because as I mentioned earlier, the basicity, a very small detection of the electron cloud from the oxygen will make it very poor base, and a little bit increase of the electron cloud on the carbon will make it a strong base, or you can say anything. So a nucleophile you can say, or a base. Okay, so it will be attacked not by this oxygen, just because it is now not normal oxygen, it is a little bit poor. It will be attacked by this or this. Okay, so that's why any electrophile, if you react it with the benzene having an electron donor, will be attached to the orthos or the para. Now we are not discussing that it will go to the para or the two orthos. Okay, So that is another subject. We'll be discussing that then. So my aim is just to make you understand that how the actual structure of those kind of the molecule will look like. So it will be like this. So again, don't be confused that those things doesn't occur, but they are necessary for us just to make us understand this. So now just let us look to another molecule. This is a benzene and it has an aldehyde present on it, and as you know that this inductive effect of the oxygen is more, so it is an electron withdrawing group by resonance, by inductive effect too and by resonance. Okay, so let me write this structure a little bit clean. Now let me write the canonical form of this structure. A lone pair on oxygen are there. Okay, so what happens? First of all, those electrons are shifted here and they sit here. How? It is just similar to this molecule, this portion. Okay, it shifts here and it sits here. And if you don't consider the other molecule, this portion of the aldehyde and this portion is just like this thing. Okay, this portion from here you go and there. Okay, just like alpha beta unsaturated aldehyde. Okay, so it will make this thing. Now the electrons will move to the oxygen. I should write those electrons on its place. Now it has a double bond, but now this has a single bond and a negative charge. Okay, and the hydrogen is on its place, but now here a positive charge appears because electron moved away from it. Now those electrons are shifted here. This is the canonical form because now positive appear here. Now I am not writing all the lone pairs because it is taking time. Okay, this thing. Again, after that structure, what will happen? This will come here and you have another positive charge appearing on what? Here in this carbon, or negative H. Don't write O without its non-bonding electron. I have short times, that's why I am writing it. Now what happens? Those comes and it sits here. Okay, and we move to the same structure again, but this time the electrons are, the pi bonds have shifted its position. Okay, so we went to the structure. Okay, now anybody who want to study it in a little bit detail, and go for my other lectures on modern concepts of organic chemistry, and they will understand all the modern concepts on chemistry. So go to the playlist and you will find that, but there I have explained it a little bit more scientifically. Okay, so this is the structure. Now in these structures what happens? Again, a positive charge is concentrated here on this position. We call it ortho. This is a para position, they call it para, and they call it anortho. Okay, so again, how would the actual structure be like? The actual structure will be like this. The ring become a little bit poor, electron deficient, you can say, poor. Those are positive. These are not positive charge, but the electron density, as you see to all those, the electron shifts from those specific carbons. Okay, from the bonds which are on those specific carbons to where? To this and to this oxygen. Okay, so I should write it like this. The oxygen is a little bit negative, or this. Now any nucleophile, okay, here it is a little bit difficult, to say, but because aldehyde is also electrophilic, but let's say you have some nucleophile, the nucleophile will move to either this or this position, okay, because they are positive, and those things we will be discussing in the chemical reactions, okay. But that will attack either this carbon or this carbon or this carbon because they are positive. Any acid, or if you want to protonate it, any acid or electrophile, suppose acid plus H plus or electrophile, this oxygen will attack it because it is more negative, okay. So now we have understood those things, and again if I write another structure, you will be very easy, you can understand that too, because I'm not going to write or draw all the structures, all the canonical forms. Now it is sufficient. Another electron withdrawing group is NO2 and double bond O negative. It has made 4 bonds, so it is negative, and this is negative because I am not writing the lone pair right now. And as you know that this electron will move and it will come here, so ultimately positive will be moving on the orthos and the paras. Its structure will look like this. Those resonance structures, those resonance type of thing doesn't occur. In actual reality, the structure is stationary electron cloud, and it's like this, okay. So those are positive sites, and this ring is very electron deficient or poor because a small portion, very small portion, just 2 or 3 or 4% of electrons are extracted out of the ring, okay. 4% of electron cloud is extracted out of the ring, okay. Now when we let me try another example. Suppose you go and see this molecule, it's called aster. Again, as you see it will shift here and it will shift here. You can draw those structures by yourself now because it needs a little bit practice, but my aim is to tell you that how the actual structure will do. This is the resonance form, but again it will depend that what is its contribution. The actual structure is again between those two, but it's almost near to this structure, okay. So what will be the actual structure of this molecule? It will be like this. Those long, if you have some acid, do not ever protonate those oxygen because now they have lost a little bit of electron density. Always protonate this thing. So if you have an acid present, it will never be attacked by those things, never ever, because it has lost a little bit electron density on to the other carbon, and it will be attacked by this oxygen, okay. So the actual structure is like this. So I should write it like big, and one of the lone pair is a little bit smaller, okay, and the negativeness appear here. It's not negative, very much negative, but you can say that it's a little bit more negative than neutral. So it will, those electrons or of the bond will attack it, okay. So you can draw it like this if you want to draw, because for the mechanism the resonance structures are very important. If you for those, okay, now you understand the reactivity. So if it went here, now this bond will attack it. So if you draw a mechanism, then you can draw these things, okay, and this will help us you to understand the reactivities of those molecules. So another example is this one. What about this molecule? If I am drawing those structures, because I think that, because in my mind it is that you have studied the previous structures and you understand that what is actual, which is good and what is bad structures, okay. So its resonance form is like this, the good one, CH2, oh I'm sorry, CH2, it comes here and it will go there. If you have this molecule, a molecule like this, these are lone pairs 3, it has a positive charge. So the actual structure, its actual structure will be like this. A little bit positive here and a negative here. So again I am repeating, those things doesn't occur, that it moves here and it is the actual, those help us to understand this structure. The actual structure is like this, that the oxygen is a little bit negative and this carbon is a little bit positive. So if you have any nucleophile, NU, it will attack this carbon, or you can say this carbon, because in the resonant form it is a little bit more obvious to you. Okay, so nucleophile will attack this. If you have any acid or something else, this oxygen will attack. How it will attack? Again, I should, because that is for the mechanism. If you have some H plus acid, if this shift here, it will, you can show it like this, it will attack it. Okay, so I hope you understand many things. So thank